So to get started here, today's webinar is one of the final steps in the Extreme Flood Vulnerability Analysis project that MnDOT led with support from WSP, and today's call will focus on sharing the methods that were used in the project as well as some of the results. My name is Siri Simons, and I'm the Sustainability Program Supervisor in MnDOT's Sustainability and Public Health Division. And while I haven't been involved in this project in the last couple of years, I'm really excited to be introducing the topic today. I was part of the team that secured funding for this research. So at the time that we looked for funding for this project, we were particularly interested in the increasing mega rain events and extreme precipitation events that Minnesota was experiencing as a result of climate change. Kenny's background shows some of the impacts of the extreme flooding that we can experience here in Minnesota. And so the goal of the project was to empower MnDOT staff to mitigate risks to our transportation infrastructure by integrating climate change vulnerability data into our asset management systems, specifically BRIM and TAMS. So this, I think, is even more timely research today as we work to position MnDOT for the PROTECT funding that became available in the bipartisan infrastructure law and that MnDOT could access to invest in assessing vulnerability in our state as well as adapting our infrastructure to our changing climate. So today you'll hear from the team at WSP that developed the methodology to analyze risks from extreme flooding to our bridges, pipes, and culverts. And before I hand it over to that team, I just want to acknowledge all of the work that the technical advisory panel put into this project. That team was led by Jeff Meek, who has transitioned out of his role at MnDOT over to a role with ICF, but was pretty critical in advancing this work. And the members of the TAP provided a lot of time, I think more time than we had originally intended for this project. And their technical expertise was really essential in contributing to the methodology and the results that you'll see today. So with that, I think I'll hand it off to you, Chris, to go ahead with introductions and sharing the presentation.
All right, thank you, Siri. Get this presentation started here. This has been really a wonderful project to work on. It's been a lot of groundbreaking work that's been done on this effort, and just really a pleasure working with the TAP and other MnDOT staff on this, because they've been so you've all been so engaged on it, and we don't see that on all of our projects with all the clients that we have, and we just really appreciate that level of engagement and being down in the technical weeds with us and understanding it, and we're hopeful that that will translate to more of an understanding of what the outputs are, and hopefully more application of those outputs, that this just won't be put on a shelf somewhere and forgotten, that there's real understanding and buy-in to the effort. And I also need to thank, of course, the team that internally at WSP who's worked on this. I'm the project manager, again, Chris Dorney, and let me go through and introduce the team members. And if you guys can maybe wave or acknowledge when I name your names, and I'll just give a brief background on their area of expertise, and then they'll present their sections as we and what they contributed to the project as we go through the presentation here. So we have Josh Amos and Greg Kornetsky. Both of them are GIS experts and led a lot of the GIS work on this project. Greg mostly in the setup of the hydrologic and hydraulic models, and Josh in the setup of the inputs for the risk model. We have Peter Enright, who's a water resources professional. He developed and refined the hydraulic models that were used on this project. And then we have Tim Gross, and Tim has a lot of background and experience with climate change adaptation and also GIS, but his biggest contribution on this project was building the risk model itself and running the risk model, and also the detour routing algorithm that we'll talk about how that worked later. And I'll just say, for those that don't know us, we're with the exception of Pete, we're all in a team at WSP that focuses on climate change adaptation. We've been doing this work for about 15 years now, and it's exciting now to be able to turn that work into more of a risk-based approach to decision making, and that's really what this effort was all about. And this flood vulnerability analysis is trying to get to a risk score for each asset under different climate scenarios. So I'll also say that the purpose of this presentation is we can't get into every little detail on the method, but it is to give you sort of a high level to moderate level introduction to the methodology. And there are other materials that are part of the project deliverables, which will get you into the nuts and bolts of how you would do this. That specifically includes an instruction manual that takes you more or less sort of step by step in how you would implement this methodology. So encourage you to look at that. And then there's also a series of technical memos that document at a bit of a higher level. It's not step by step, but it's still pretty detailed, sort of the conceptual approach. So again, encourage you for those who are interested in learning more or eventually might actually implement some of this model to look at those documents. In this presentation, we'll start with an introduction to the project. From there, we'll go over the methodology, and it really breaks down into two phases. The first phase is the flood exposure analysis, just trying to understand what the probabilities of flooding look like at each asset. And then phase two is the risk analysis or calculation of the do nothing costs. If no adaptation actions are taken, what we try to do here is come up with an estimate of what the cost might be to both MnDOT and the system users, and that is what the risk is. So we'll talk about that after we talk about the flood exposure, and from there, then we'll conclude with the next steps in the implementation process. All right, so a little bit more background on the project. As Siri was saying, the motivation for the project is a recognition that we've seen in Minnesota an increase in extreme precipitation and flooding events that have, in some cases, caused damage to MnDOT assets. And we want to understand in an efficient manner how that flooding threat will evolve as climate change continues to happen. And we need this to be in an efficient manner because we eventually want to study all of the bridges, all of the bridge culverts, and all of the pipes on the state highway network in the state. So we're talking thousands of assets. And so that need to eventually scale this up was very much a part of the development of the methodology and trying to automate as much as we could. So there are still some manual efforts that are necessary, but scaling and being efficient is a key part of this. And again, those are the three asset types that we'll focus on. And there are still some of those assets that the method is not applicable to. Those include bridges that are on large rivers with drainage areas that are exceeding the regression equation maximums. This methodology is dependent on use of the regression equations that are available through the StreamStats program. So if you're on a river that's too large for those regression equations to apply, that basically is the portions of the Mississippi, the Minnesota, the St. Croix, the Red River, and the Rainy River, uh, this method's not going to apply. And likewise, on the opposite end, very small pipes with drainage areas smaller than a regression equation minimum, the method that we're going to go through here doesn't apply to those either. So we have sort of developed a scope, a proposal for how you would do those smaller pipes, but we haven't actually undertaken any work to develop that methodology. Largely, the methodology would be mirroring what we're going to talk about now, with some amendments to it to deal with the fact that we can't get peak flows out of stream stats for those small drainage areas. We are, one of the first steps in the project was to confirm, though, that this belief that, hey, climate change is going to create more intense precipitation, greater precipitation depths for a given duration, was in fact true. So what you're looking at here are some of the efforts that were made early in the project. This was actually done by a staff person who's not on this call, Rawlings Miller, to develop precipitation projections. And what we did is develop 24-hour duration precipitation depths for several different return periods. We need to use probabilistic data for the risk assessment to work. And so you can see all the return periods that we generated precipitation projections for, 2-year through the 500-year event. What I'm showing here on the screen is the 100-year return period event, and the map on the top left is what we look at today. Here's the legend, and then we had 2 climate scenarios that we looked at on this project. Representative concentration pathway 45, and you can see how that evolves over time. These are the different years in the horizon years that we looked at. So we took it out to the end of the century. This is a climate change scenario that it generally involves lower greenhouse gas emissions than the trajectory that we're on today. But you can still see, even with that, we see an increase in precipitation depths, particularly at the 100-year event, particularly in the southern part of the state. And this is RCP 8.5. This is the more pessimistic climate change scenario, where we have more greenhouse gas emissions, sort of, in some sense, perhaps mirroring the trends that we're on now. And you can see that results in even greater increases in precipitation depths throughout the state. So there's a tech memo in that compendium of tech memos that I mentioned earlier that goes through all the climate projections and how they were created, and has maps like this for all the different return periods. So I encourage you again to take a look at that if you're interested. And essentially, the bottom line is the actual work there confirmed that, in fact, in most of the state, as we go into the future with climate change, we expect to see greater increases in precipitation depths. So I should also mention, I should mention this at the beginning. We'll pause for questions at the end of each section. So in a couple slides here, I'll pause for questions if you have any on this section, and we can address them then. Okay, so one of the things we wanted to do is, before we get immersed in the methodology, is give you a sense of what do the outputs of all this look like? What are we working towards? And it kind of boils down to 2 pieces of information, 2 sets of information. One is flood exposure data for each asset, and the other is flood risk data for each asset. Those are those do nothing life cycle costs through the end of the century that we're projecting. And again, all of this information, as Suri said, We hope to eventually be able to integrate into BRIM and TAM's hide infra for the assets. I'm not going to go through all the details here on what these outputs include, but I'll just try to give you a flavor. So the flood exposure data, this is a table for a particular, in this case, a pipe. And what it's telling you is some sense of what the flood elevations are upstream or right at that asset, and the coloring, what we're showing here with the colored text or the colored cells is whether with the colored text is the approach roadway inundated, and with the colored cells, it's yellow if we're hitting the low chord of a bridge or the top of a culvert, and it's red if we're actually overtopping the bridge deck or the road right above the culvert. And so you can get a quick visual for different return periods and different climate scenarios and different future horizon years when we start hitting key thresholds. So that's one set of information that can go into BRIM and TAM's hide infra. The other is the output of the risk assessment, and this is just a sort of a conceptual table of what that would look like. But we actually provide for each climate scenario the total expected costs, a median value, and then also a range, a lower and upper confidence interval, because obviously there's a lot of uncertainty with any effort like this. So we try to give some range to that. And then we break down the cost by whether those are costs that are likely to be borne by MnDOT, i.e. physical damage costs, or system users, because they have to detour around an asset that's been damaged or closed due to flooding. So that's also information that can go into BRIM and TAM's hide infra. And then how can you use this information? There's really a myriad of different uses for it. Here are a few. One is that you can use it to prioritize assets for more detailed, what we call facility level adaptation assessments. And those assessments I'm showing covers from a couple that we did on a previous project with you guys at MnDOT. Those assessments really home in on a specific asset or maybe set of assets that are in close proximity, and say and do a more detailed engineering kind of conceptual engineering level investigation of are we going to see issues here? Take those climate projections, maybe run it through some more detailed modeling, and then if we are, actually look at what are the adaptation options that we could implement at each site, and then it involves a benefit cost analysis to determine what's the most cost-effective adaptation option for each location. And so we have these two studies that were done up in District 1 and District 6, if you want to look at an example of that. But these results, the risk results, can be used to help prioritize the highest risk assets are the ones you may want to look at doing those studies first. Ultimately, once you've done those studies and identified, hey, this is the action that makes the most sense financially and otherwise, and there's also qualitative considerations, things like environmental considerations, socioeconomic considerations that need to be considered. Ultimately, you can have an actual project that you could program and put in your construction program. So that's one potential use case. Another is this data can be integrated into the transportation asset management plan, which provides another route for eventually getting into the projects into the construction program. The information can also be used to inform emergency response. For example, identifying assets that are candidates for upsizing should they get damaged. You could work with first responders to look at if there's a particularly vulnerable community that may be cut off by the only access points are through these particularly high risk assets. So it's information that can be shared with first responders and emergency response planners to inform their efforts. And it can also be used to identify potential enhancements to operations and maintenance activities. So things like pre-planning detour routes, or maybe high-risk culverts get priority for cleaning, that sort of stuff. You can think about those as being potential use cases for the data as well. So, and I'm sure there's plenty of others. Let me pause here and see if there's any questions before we dive into, at least giving you an overview of the methods to get to those results I was sharing. Any questions?
I had a quick question.
Sure.
Will you go back to the methodology a little bit, or the equations? Yeah. So, yeah, one more forward. So thinking about the software, actually slide like 4, maybe, Chris. There you go. Yeah. So like here is the calculation showing, is that the size, the RCP 4.5 and 8.5, or what are those?
Those are the two climate scenarios
Okay.
that I was talking. So the RCP 4.5 being sort of a moderate or lower climate scenario, and RCP 8.5 being a higher climate scenario, higher greenhouse gas emissions. And generally this doesn't always hold up everywhere in the world, but in Minnesota it does generally. That 8.5 has generally a greater increase in precipitation than 4.5, but both are increases over current day.
So would you be applying like the same model, but just different elevations depending on the culvert surroundings, or what? How would what would the logic look like? Would it be different for each culvert?
Mm-hmm. Well,
Yeah.
Yeah.
Yeah, each culvert is, and we'll get into this as we go through the method. There's a Pete basically has set up and developed sort of an automated HEC-RAS tool that runs HEC-RAS based on, at a sort of higher or moderate level, not a design level, but runs it at that level based on a variety of, inputs that are specific to that location and the design of that particular culvert or bridge.
I'm getting ahead of myself, but I'm just thinking about how you would implement this in a software. Thanks.
That's all part of it. And so it is a software that is available, and it uses the data that's available to us from the MnDOT databases, and so it sort of customizes the analysis to each location, but it's the same model that's used, and then we feed it these different different peak flow inputs that are specific to that location as well. So
okay, thank you so much.
Same model, different inputs in each spot based on its actual design and environmental setting. Any further questions at this point?
This is Kenny. I had my hand up. I'll just put it down. Just real quick, RCP is a representative concentration pathway. It's based on, if you drive in the models, the greenhouse gas concentrations, so that they reach an equilibrium equivalent radiative forcing. In other words, how much potential warmth you get globally. 4.5 stands for 4.5 watts per square meter, and then 8.5 is the much higher greenhouse gas concentration scenario, and that's 8.5 watts per meter square. That's all. So it's a kind of, so we say these scenarios mean, basically at 4.5, things would stabilize around 650 parts per million of carbon dioxide, and that would be equivalent to maybe around 50% more than our current concentrations. And at 8.5, it's a much more dire, even more extreme scenario, such that the radiative forcing is almost twice as high. That's all. It's very technical, but you see these numbers and terms all the time, RCP. So just thought I'd throw that in there. I'll put it, got it in the chat.
I'm sure everybody knew that exact thing that you just said.
Yeah, especially the, equivalent equilibrium radiative forcing. That's a fun one.
I was just
Sorry.
like, wow. Okay, great. Thank you.
Yes, we appreciate that. And yeah, there's definitely a lot of background material there to read up on. And one source you can start with is the tech memo, but there's obviously, which touches on this a little bit, but there's a lot more depth of information available from the UN's IPCC, the Intergovernmental Panel on Climate Change, and others. You know, if there's any questions about where to go, we can help refer you to that to get up to speed on sort of the climate science 101. I should also say that one of the reasons that we chose these two scenarios because there's a lot of different scenarios that you could look at. There's 3 or 4 different RCPs, and then there's also within each of those, there's multiple climate models that are run to, and each climate model from a different research organization has a different take on what that particular amount of warming means to precipitation change and temperature change and so on and so forth. The tech memo goes through, you know, the process that we went through to evaluate all those different permutations and boil it down to 2 that sort of give some sense of the bounds. You know, it could be, again, these are not the absolute bounds, but that's the idea, is to generally give some sense of, you know, this is the more optimistic projection, this is the more pessimistic, some sense of bounding the future. So that's the overall philosophy for choosing these simulations and you know, ideally we'd love to run all of the simulations through the whole process that we're going to talk through, but then we'd still be working on this, you know, for a few more years probably to do that. So you kind of have to boil it down. So.
Well, and I think it's important to note, just for context for people, is that in the terms of being optimistic, what we're saying is that the world transitions away from fossil fuels and carbon emissions. And that is important context to know, kind of, it's in the world's control potentially, but these are still just predictions. And so it's really hard to know what's going on, but it would be really nice if we keep pushing further away. And 4.5 is basically saying that we make some strides in transitioning away from fossil fuel use. And 8.5 is really saying we're not making much progress. So.
Yep. Thanks, Chris. All right, well, in the interest of time, let's cut to an overview of the methodology. So again, as I mentioned, a hallmark of this project is we took a quantitative risk approach. You know, I mentioned the earlier project that involved the facility level assessments. There was also a systems level assessment there that used a different approach, what we call an indicators approach, that, you know, sort of the state of the practice now, but we wanted to go state of the art and use this risk approach. And the main advantage to that is, you know, the indicators approach basically just gives you like an index score that can be a little bit hard to interpret, whereas the quantitative risk approach sort of forces you to make the connection between different flood levels and critical physical impacts and what those costs might be. Obviously, there's a lot of uncertainty involved in all that, but it forces you to make that sort of real world connection of, you know, what does this flood level mean in terms of damage to the asset, and then what's that mean in terms of cost? And that's what we try to get to is when we speak of risk, is it's really an expected cost over a certain period of time if no adaptation actions are taken. And there's another advantage to having it in the format of a dollar value, and that's that, you know, that can be easier to communicate perhaps to decision makers and others who might want to use this data, you know, that are used to working in the dollars and cents. So these cost estimates, as I mentioned earlier, include both damage and repair costs to the assets from flooding, and those are costs that would, since these are owned by MnDOT, would be borne by MnDOT. And they also include costs to systems users. These are costs due to the delays of not being able to use that asset and having to divert around it. So let's talk about each of those a little bit more. The physical damage cost, the physical damage assessment, Again, we looked at damage costs to each asset from the projected flood events. We calculate these costs for each of those different time periods and each different climate simulation. There were three different models that basically calculate these costs. One pertains to culvert damage model, only to the bridge culverts and pipes, and the other, the bridge damage model, obviously pertains just to the bridges. The roadway damage model is the third, and that actually pertains to the approach roadway, so that's pertinent to both the culverts and the bridges. And so the roadway damage model, it looks at these sort of physical damage mechanisms: pavement delamination of the roadway due to the flooding, and erosion of the embankment due to the flooding. Culvert damage model, we're considering the loss of the culvert, or sorry, the loss of the culvert due to embankment erosion. We're also considering outfall erosion around the end of the culvert and what damage that could cause. And the bridge damage model, that's looking at pavement delamination on the bridge itself, also potential deck damage or displacement from water hitting the deck, and then scour as well, for both pier scour, abutment scour, and contraction scour. All three of those are considered. And again, there's a whole tech memo that gets into a pretty good amount of detail on the methodology that's used and the equations that are used to do these damage assessments, all of which is sort of embodied in the tool and the code that Tim will talk about later that does the risk calculations. Again, the other part of that risk score is the user impact costs, and what that involves is, again, estimating the cost to the traveling public for detouring around flood impacted asset. It considers, basically, there's a custom designed detour routing tool that's been developed and you can run in GIS that Tim's created, and it says, okay, if this segment of road is flooded, what's my shortest path detour around there? And so once we know that, it considers, we consider the traffic volumes that take that road that's been affected. We look at network redundancy. That's that detour path. We consider the how long it's going to potentially be out for, and then time, fuel, and operating costs from MnDOT guidance to basically compute what the cost of that detour might be for any given flood event. And again, this is just a rough estimate. There's obviously other costs, other user costs that we're not even considering here. Even within this cost, there may be additional costs due to congestion that's caused by the detour. We're not able to get to that yet in this sort of 1.0 approach, but it's a start to try to capture and give some sense of system and network redundancy and what the users may experience from an outage. We then essentially take those physical damage and user costs and conceptualize this as a curve, like a depth damage curve that considers both of those. For a given depth of flooding, here's what those costs are. And that's sort of fixed for the asset. And then for every given horizon year that we're looking at under each of the two scenarios, climate scenarios we're looking at, we can develop an exposure likelihood curve or graph as well, which relates the depth of flooding to the flood elevations to the frequency of it. And of course, again, that's going to change every year as climate changes. It's going to be different for the different climate scenarios. And then we can combine that information mathematically to plot a damage versus year points at every for every year that we analyze. We can plot a point of what the damage costs are and what the year is, and then essentially connect the dots and form a curve. And then what happens is to get the total expected flooding costs or the risk for a particular asset under a particular climate scenario, we just find the area under the curve. That's what that represents, is that total expected flooding costs through the end of the century. And this is another one of the tools that Tim will talk about that he's developed, does all of this math ingests all this information and spits out those risk scores. So I'm going to now hand it over to our technical staff to kind of walk through the steps in the methodology so you get a flavor for what's involved. We'll start with the flood exposure analysis, we'll call phase 1. We'll talk about preparation of the hydraulic model inputs first. We'll talk about how you run the hydraulic model. And then we'll talk about how you incorporate those hydraulic model outputs back into GIS. Then we'll move to phase 2, where this is, again, the risk analysis and calculation of the do-nothing cost. We'll start with how we prep the risk model asset data inputs. From there, we'll actually talk about the user data inputs to the risk model and how you get those together and calculated. And then we'll talk about how you run the risk model to generate the cost estimates. So before we do that, and I wanted to ask again, pause again for any questions about the overall methodology. Any questions about that?
Hey, Chris, Phil Schaffner. Good to see you.
Hey, Philip.
Question on the risk model and the inputs on the cost side. Are values for travel time costs and discount rates and things like that get updated every year? Are those easy inputs to adjust in the risk model, or are they hard coded in and not something that we can easily adjust as our understanding of costs change?
Yeah, I believe those should be fairly straightforward to adjust, but I'm going to kick that one over to Tim to add any details or different thoughts on. Tim?
Yeah, you can adjust them pretty easily. There's actually a spreadsheet that I'll just talk about that kind of compiles all that information, all those unit costs into a kind of dollar per minute value and a dollar per mile value. And so that's just a spreadsheet that you can input those updated parameters into. And then, of course, that needs to be fed back into the overall calculation of risk. So just things need to be rerun, but it's relatively easy to update in the spreadsheet format.
Thanks, Tim.
Okay. All right, well, let's dive into the details here, and we'll start again with preparation of the hydraulic model inputs. And I'll turn it over to Greg to talk about that work. This is a GIS heavy exercise. So, Greg, you want to?
Yeah, thanks, Chris.
Go out here for a second to
okay.
My camera off.
Yeah, so what I'm going to describe here is, as Chris said, it's GIS heavy. Almost all the work is done completely within the ArcGIS platform. For this project, we're using ArcGIS Desktop 10.7. So it's basically everything is done within ArcMap and ArcCatalog, using a lot of the built-in geoprocessing tools, and utilizing a lot of custom Python scripts that we've developed that automate and do a lot of analysis that would not be practical to do, or is not possible to do with one of the off-the-shelf or the built-in tools. So next slide. So I'll just go through like the required data inputs that help us like establish essentially what is a model of the environment that enables us to basically kickstart creating all the stuff that we're going to need to do the hydraulic modeling to come later. And so to set all this up in GIS, we start with a digital elevation model. And for that, we're using the MnGeo LiDAR project data. It's all at 1 meter resolution. And for our pilot project that only involved 22 assets, I downloaded only the LiDAR DEM tiles that were necessary to cover the vicinity of those assets, and we mosaic them together to create a a seamless mosaic. And in the future, as you do other parts of the state, looking at other assets and so on, you can create what you need to cover those areas, and even go as far as to create an entire statewide mosaic when you have the time and effort to put into downloading all that information and creating it. One of the next GIS data that you need are the MnDOT stream crossing assets, and this is what Chris had presented earlier. Like, we're looking at bridges, we're looking at bridge culverts and pipes, and all that information comes from your organization. I think the pipes data comes from your TAMS database, and all of that is depicted as points. And in the attribute tables, you have your MnDOT attributes, and you also have the MBI attributes in the cases of bridges and bridge culverts. And those give us, in particular, a lot of the information that's necessary to do this analysis, like the structural dimensions of the asset and other physical characteristics. We're looking at bridge width, bridge length, bridge construction type, looking at pipe shape, pipe construction materials, and width, and so on. So all that information is important to enable Pete's hydraulic model to do what it needs to do. The third major input here are the road center lines. So to do this correctly, you really need to have all the roadways represented by a center line, including a dedicated center line for multiple carriageways. So there is no off-the-shelf road center line data set that was appropriate and ready to go. So we actually used MnDOT's a few of your different road center line feature classes and basically integrated them together to get exactly what we needed for this project. And we also incorporated HPMS information into the road center line attributes. The fourth item that we have on here are the stream flow lines. This is basically the representation of all the streams and rivers in the state. And as Chris had noted in the introduction, we're using USGS stream stats to do most of this work. And to be able to do that, it's interesting because US Stream Stats is based on a raster stream grid network, and we actually need vector representations of those stream flow lines. So we coordinated with Chris Sanaki of the USGS Stream Stats. Well, he's a USGS guy there, but he also helped create the Stream Stats program for Minnesota, and I coordinated with him, and he was able to go back in the archives and get us a lot of the, almost all the data, GIS data, that the StreamStats application runs on there. And with that information, I was able to convert the raster streamlines to vector stream flow lines. And it's important that they not only be vector lines, but that they be digitized in the direction that the water is flowing. So you can see in the screenshot on the right-hand side there that the arrows indicate the direction of flow along all those streamlines. And we also use the data that he provided to determine the stream order of all those streams. Another required input is land cover data. The land cover data is ultimately used to be able to determine the Manning's roughness coefficient along the landscape that the stream or the river is flowing through. And we obtained that basically off the shelf from the University of Minnesota. There's a statewide data set that's at a pretty coarse resolution, but there's also some high resolution pieces of the state that we incorporated. And so we basically mosaicked all of them together and had to do a little extra work. They weren't ready to go straight off the shelf. They used a different classification scheme for their land cover code. So I essentially mosaicked all those, allowed the high resolution areas to take precedence over the low resolution areas as well, and put all of them into a common land cover classification scheme. another required input is the precipitation depth data. So we have precipitation depth data for current conditions, and as well as future precipitation depth data that comes from the global climate models. So the current precipitation depth data is coming from NOAA Atlas 14, and the future precipitation depth data is coming from the CMIP5 local LOCA data. And then besides all of those required inputs, it's just good to have what are pretty much common tools for probably just about any of us, especially GIS people, but just supplemental data sources to use for reference. And that's aerial imagery, oblique imagery. You can use Google Earth, Google Maps, Google Street View, National Hydrography data set, your own state's hydrography data from the DNR. All that stuff just helps you get a better perspective and understanding of what's actually going on in the environment there. What the bridge really looks like. Have conditions changed over the years? Maybe perhaps your the bridge GIS data that you guys have is maybe stale, or maybe it's newer than what's depicted in aerial imagery and so on. So having all that stuff at your disposal just makes it easier to get a better understanding of the real ground conditions at each of these sites. Next slide. Okay, so given all that data, now you need to create some new data that will refine our understanding of the environment here, and which will ultimately enable us to create the inputs that are going to go into Pete's hydraulic model, which he'll discuss next. But so one of the fundamental items here is the MnDOT stream crossing asset depicted as a point, and it's important that we take that point. That's pretty much the way it comes from your organization, and that we go through the effort to actually snap it to the intersection of the stream it conveys and the roadway that it carries. And if the way it's provided, it's generally very close to where it should be, but we're saying that we want to basically make it agree with these data sources that we're using, the stream stats, stream lines, and so on, and the road center lines. And so we want to actually physically snap that point to the intersection of those two features. And when it's snapped like that, it makes everything easier to it basically creates this spatial relationship that makes it easier to transfer information among the asset point, the stream, and the road center line, and these other elements I'm going to describe next. And so one of the things we need to determine that unfortunately is not built into the stream stats streamline data is the slope of the stream in the vicinity of the subject stream crossing asset. So there's a multi-step process to use the elevations from the DEM to determine what the slope of the stream is. Basically within 600 feet or so of the asset. That's basically the area of interest for this particular exercise, is determining that slope. And then we create a cross section. We're going to create two stream cross section lines. So we create one upstream of the asset that's on the left hand side in this particular screenshot, and we create another cross section just downstream of the asset on the right there. And you'll see that if you can discern it in this snapshot here, that the directionality of the road as well as each cross section is important. A lot of the models and the tools expect that the orientation will be from left to right, facing downstream in its direction of flow. So that you can see there's a little arrowhead on each of those cross section lines, as well as the road center line that's going across the asset there, indicating that they're basically orientated from left to right in the direction of flow of the stream. So those two cross sections basically allow us to describe the boundary conditions just upstream and downstream of the asset, and that'll be important for the hydraulic modeling. So once we have those two cross sections established, we can basically cut an elevation profile along them. And that's what I'm depicting here with these two little profile depictions that we see here. So at each one of those, at each station along each of those cross sections, we're basically using the resolution of the digital elevation model. So you're getting a point sampled every 1 meter along that cross section line, starting from station 0 and going to the end of the line. And so you're getting, not only are you getting the elevation at each point along that cross section, but we're also using the that land cover data to extract what the land cover classification is along that. And then we eventually transform or derive from that land cover data what the Manning's roughness coefficient is at each location along the cross section too. And we do a similar thing for the road center line that stream crossing asset is conveying. So we looked, generally some distance, to each side of the stream crossing asset, and we extract the road center line from that, and then we say, hey, let's cut an elevation profile along that road center line, and that's the profile that we're looking at in the center of the three profiles that are stacked there. And the Manning's roughness coefficient isn't important for that, so we're basically just looking at the elevation at each location along the road there. And I was also going to indicate that at each one of these positions, we're also going to apply the stream slope that we had calculated earlier to each of the two cross sections, and that will help the hydraulic modeling tool do its work. So, as we've already said, a lot of this work relies on the USGS StreamStats application to get current peak flow statistics. So we use the StreamStats application to get not only the current peak flow statistics, but also a drainage area polygon. And we get that at each of the three locations here, like at the upstream cross section, at the stream crossing asset itself, and along the stream at the location of the downstream cross section. So at each one of those, we get a suite of peak flow statistics for different return period events, and we get a drainage area polygon from StreamStats. And if you're a StreamStats user, perhaps you're familiar with using like the web-based interface where it's it's a interactive web map, and you go there and you click on one of these streams that are part of the StreamStats model. You click on the location where you want to get information, and eventually, after several minutes, it'll do all its work and kick back either a report for the information that you requested, among them the peak flow statistics, if that's what you chose to ask them for. And you can also download data from that. But that sort of thing, we're trying to do stuff at scale here, trying to process many assets at once. So we actually use the StreamStats batch processing tool, which allows you to create a GIS shapefile of points that are snapped to these streams, and you can submit all those points, and eventually you'll get an email saying that your batch had been processed and it's available for download. And that's the way we do this automated GIS approach to process a lot of assets at once. So, and then another thing that's not depicted here, but we also are interested in the future peak flow statistics at each of those locations, at the upstream cross section, the stream crossing asset, and the downstream cross section. And I've reserved a slide that will come later to discuss how we estimate future peak flow statistics. And then the last element here that we create is what we call a watershed storage series. So this is a technique to refine the future peak flows that will be flowing through the cross sections and the stream crossing assets. The flows that you get from StreamStats and that are derived from StreamStats are deserving of some technique to refine. And the way we do it is we like to look at the drainage area that's upstream of the asset and determine what the water storage capacity is for different flood elevations. And all that's done in GIS. So we, for instance, we'll look at we'll start about 5 feet above the road elevation above the stream crossing asset, and we'll see what the volume of water that can be stored upstream of the asset in the drainage area. And then we'll go down in 6-foot increments until we reach the top of the roadway, and then we'll keep going lower than that and until there is no more water storage capacity. And that series of metrics enable Pete's hydraulic model to better determine the effect of the attenuation of the flow as it goes through the stream crossing asset in that environment. Next slide. Okay, so this is just basically an enumerated or numbered thing here that describes a lot of the things I just went over. So I'll just go through it quickly here, but these are the general steps that we do. We snap the stream crossing asset to the intersection of its road center line and the stream it conveys. We determine the slope in the immediate vicinity of the stream crossing asset. We create the 2 cross-section lines there, the upstream cross-section line, the downstream cross-section line, and we cut an elevation profile along each of those cross-section lines that not only includes just the elevation, but also includes the land cover classification, and from that we derive the Manning's roughness coefficient. And then we do essentially the same thing for the roadway there. So we create a profile along the road center line that's carried by the stream crossing asset, and we get just the elevation profile there. And then at each one of those 3 locations, the upstream cross section, the downstream cross section, and the stream crossing asset itself, we query the USGS StreamStats application via its batch processing interface to get the suite of peak flow statistics at each of those locations. And as we get that, also include in the output are the drainage area polygons at each one of those 3 points that we queried. And the next step is then to transform those current peak flow statistics that we got from StreamStats into future peak flow statistics. And to do that, we use the StreamStats peak flow statistics along with the current precipitation depth values that we get from NOAA Atlas 14, and we also use the future precipitation depths that we get from the global climate models that we're using. And there's a slide dedicated to that to come, so we'll get into the details of that. And then once that's done, we do this watershed storage capacity series that I had just described on the earlier slide. And all that information is kept in a table. And then essentially what we do from there is we're going to temporarily transition from the ArcGIS environment to the hydraulic modeling environment that Pete's going to describe. And going between those 2 environments is basically as easy as saying, from my GIS shapefiles or feature classes, I want to export their attribute tables to CSV files. And those CSV files will be ingested by the hydraulic modeling tool, and it will do all its work. And so that's, for instance, that's the it's the attribute table for the stream crossing asset that includes, it's composed of all of the fields that come from MnDOT that describe the asset itself, and it's supplemented by the current and future peak flows. And then similar thing is done for the cross section lines. We have, it's the cross section line, it's the slope at that cross section line, and it's the current and future peak flows at that cross section line. And then we also have the elevation profile along each of those cross section lines and the road center line itself. So essentially this information is maintained both in, in a GIS format where there's a spatial component to it. There's actually a cross section line, a line feature. There's also the elevation profile along it is also depicted as, GIS points, and but everything that's going to go into a hydraulic modeling tool is just basically purely tabular data. And for instance, the hydraulic modeling tool can use the elevation profile, because the elevation profile has attributes that say, okay, I'm a point X distance from the beginning of the cross section line, and my elevation here is this value, my land cover value is this value, and my Manning's end value is something else. So just using that tabular data, and this is true of a lot of programs, you can recreate or regenerate that profile into something that's tangible and useful for analysis, like is being shown on the screenshot, where it's just tabular data that was used to generate that profile there. And so all that information will go into the hydraulic modeling tool, and then we'll come back. The hydraulic modeling tool will give us the outputs. Among them, probably the most familiar thing is going to be like what is the floodwater surface elevation at all of these different scenarios that we're looking at, and that will come back in a table. And once we get that brought back into GIS, then we can do some more analysis. For instance, like what's the depth of flooding along this roadway for a particular for a particular out year and particular event. All right, next slide. Okay, so this is just one of those slides I chose to take a closer look at using stream stats and obtaining the current peak flows. So again, using the batch processing tool, we're looking at these 3 points here, the upstream, downstream cross sections, as well as the stream crossing asset. And we're saying, hey, stream stats, give us the peak flow statistics at each of those locations. And inserted there is like a little screenshot of what stream stats will give you back. It'll say for a particular, for instance, this is a pipe, so it's saying, okay, for pipe 226 1376, the peak flows for the 1 and 1.5 return period event are 33.7, and they give you, those are the return period events that are available for the state of Minnesota, going from 1.5 up to the 500-year event. And so and the next 2 rows below that give you the same information for the upstream cross section, the downstream cross section. And also depicted on that screenshot there is the you can see the boundary of the drainage area polygons. There's actually 3 of them stacked on top of each other there. The upstream one cuts off right at the upstream cross section. The one at the stream crossing asset extends a little further, and the third one extends all the way to the downstream cross section to the right there. So next slide. Okay, so as we were saying, a lot of this is based on stream stats, because the current peak flows that we get from stream stats eventually enable us to estimate future peak flows for all these future climate scenarios and conditions that we're looking at. So the flow scaling technique is interesting because it's sort of like a simplified way to get to future peak flow statistics along a stream using current peak flow statistics, current precipitation depths, and future projections of precipitation depths. So the flow scaling technique here, I've outlined it here, says, starts with number 1, which we already talked about. Let's get the current peak flows for these return period events from stream stats. And then let's get our 24-hour duration precipitation depths from NOAA Atlas 14. So these are current, or AKA historical observed precipitation depths that are coming from the NOAA Atlas 14 data. So we download all those rasters. We use the drainage area polygon that we get from stream stats that comes back from the batch processor, and we say, hey, within the drainage area for this particular asset that we're looking at, let's calculate the area weighted mean precip depth from that raster. And let's get that for each of these return period events. And so you can see that we've listed them in this slide, 2, 5, 10, 25, 50, 100, 200, 500. And then what we'd like to do is associate the current peak flows with the current peak precipitation depths in that drainage area. So perhaps a little bit difficult to see here, but that association is being made and depicted on this this example graph here with the orange points that are on there. So we're saying, hey, for instance, for the 100-year event, which is at the intersection of those two yellow lines there, we're saying if NOAA Atlas 14 is telling us that the precipitation depth of the 100-year event is 5 inches, and USGS StreamStats is saying that the peak flow for the 100-year event is 1,000 cubic feet per second there, then that's the relationship we're gonna make there, and it's all based on the assumption that the current precipitation depth is you're able to establish. You're saying that the flow for that return period event is the flow for that return period event. So if it's a 100-year event and the precipitation depth is 5, then you're saying, oh, well, I'll just look up the 100-year event in StreamStats to get the flow there, and that will be the association that we make. And once we've plotted all those orange points there, we can then basically interpolate between them to create this graph here. And once we have that graph established, we can say, okay, now let's go look at the future precipitation depths that the global models are global climate models are telling us of. So we look at the global climate models and we say, okay, we've extracted from you the 24-hour duration depths for essentially those same return period events, and we're looking at these. We're looking at these 3 horizon years. We're looking at early, mid, and late century time periods, and we're looking at these 2 RCPs that we had discussed at the outset of the call here. So we're essentially looking at 48 different scenarios that we're looking at here. And once we have those depths, we can basically use this graph as a lookup table or a lookup graph and say, okay, well, if the future precipitation depth is telling us that it's going to be 6 inches, we can just go to the 6-inch mark here along the horizontal axis, and we can go up to the graph there and say, okay, well, that's where where it intersects the blue line there. That'll tell us what our estimated future peak flow will be for that return period event at that out year and for that RCP. So this, by the way, is not being strictly done in GIS. We have a very handy Excel workbook that does all these statistical calculations. So we essentially transfer the current peak flow data that we get from StreamStats into the spreadsheet, along with the precipitation depths that we're getting from the current stuff from NOAA Atlas 14 and the future depths from the climate models, and we just plug all that into the spreadsheet. The spreadsheet essentially calculates or dynamically generates this graph on the fly and tells you what the future peak flows will be for the suite of return period events that we're looking at. And one more slide, please.
Hey, Greg, this
Yeah.
is Siri. I'm just popping in with a quick time check. We're coming up on 12:15 Central Time.
Yeah,
So
this
we've
is my
got,
last one. So.
okay, great. Yeah, just a
Thanks for the heads
reminder
up.
to be mindful of time,
Yeah.
maybe keep it to 1 to 2 minutes per slide.
Yeah,
Thanks.
this is the last slide in my set here. So this is just taking a closer look at the watershed storage series I had talked about earlier, but those little screenshots are basically from left to right saying, okay, at a certain elevation above the roadway, in this case it's a pipe, what's the volume of water that can be stored within that drainage area. And so as you proceed to the right, you're basically going down in 6-inch increments, half-foot increments, until there's no more storage capacity at all. And so that's why that red area that's indicating the area in which the volume of water is being stored eventually diminishes to nothing. And it's all that all those metrics are basically embodied in a simple table that's provided to the hydraulic modeling tool that Pete's going to discuss next. So that completes my section there.
Thanks, Greg. Chris, are we going to have any questions for Greg before I get started?
Sorry, I need to go off mute and get out of there. Are there any quick questions for Greg? Shall we continue in the interest of time here?
Yeah, we can regroup for questions after. Maybe what Pete describes what he has. That'll give a better understanding and allow us to kill a few questions.
Okay, let's do that. All right, take it away.
So based on the inputs that Greg's described, our process is basically to now automate the creation of HEC-RISE models for a few different types of situations. So we have kind of the way it's set up, there are like template input files for the HEC-RISE models, and we've created a tool in Microsoft Excel that takes all the input data that gets generated from the GIS pre-processing steps and converts all of that into HEC-RISE models, kind of using these almost template projects, and then kind of modifying them to create the HEC-RISE models for each of the specific cases, whether it's a cross section for an open flow section of the river, a bridge structure where you have a deck and then flow underneath, or something like a bridge culvert or pipe where you have a specific kind of size of conveyance and everything else is kind of obstructed below a certain elevation. So the tools allow both kind of the input and the output to be looked at by the user before we kind of move on. So it kind of gives you the ability to kind of vet things as you go. And we'll get into that in a little bit more detail. But basically, there's an input process where you bring the information in. You can look at how it's being kind of analyzed and pre-processed. The HEC-RISE models get run, and then you can look at the output at the end before you then pass it kind of down to the kind of post-processing, which we'll discuss later. So next slide. Thanks, Chris. So this is just a quick look at the input process. So kind of first tab on the sheet here, there's a couple of very familiar type of interfaces where you click on the open folder button and it'll allow you to navigate to where those files that you've generated from the GIS pre-processing are stored, and you select that folder and then it'll kind of populate this table here that shows kind of all the files that's detected in that folder. And then you can, from that point onwards, refresh the queries within the spreadsheet that bring in all of that information after you've kind of validated that you've found the right folder. And then that will allow you to kind of step through the tables of that input information to see, okay, yes, is it being reflected correctly? And are there any errors that are cropping up as it's pre-processed? The main thing to check in this instance are things like the geometry of the cross sections that are coming in. So make sure that what is being reflected in the spreadsheet is not detecting any errors such as partial cross section data coming in from GIS or something like that. And then also making sure that the information about each of the assets that you're looking at is kind of within the realms of sanity. You don't want to have culvert sizes and things that kind of seem unrealistic. So it's always good to perform a bit of a sanity check on some of those inputs to make sure that there aren't any kind of mismatches in terms of units and something is entered incorrectly in the database and needs to be addressed before you kind of move forward with the model runs. Finally, you can kind of look at the flow scenarios as well to make sure that those are coming in correctly and there aren't any missing or any numbers that you think kind of look out of this world before you hit run. So next slide, thanks, Chris. So there's two modes that you can run the model in. One is kind of cross sections only or full asset analysis. So this kind of allows you to break up the process a little bit into kind of two steps if you wish. If you run a full asset analysis, it will run the necessary cross sections for you in order to process the assets, because we need to run those up and downstream cross sections in order to understand how the each of the assets is going to perform. But if you wish to run the cross sections first, so that you can get a sense for if the results are coming out as expected and kind of work through any areas, then you can just run the cross sections initially to get a sense for how things are looking, and then it won't rerun those, and you can kind of pick up where you left off, so to speak, and just run the asset part of the analysis with the information that you've already populated from the cross-section run. So there's a couple of different modes that you can use the spreadsheet tool in. And then there are also simulation parameters that you need to specify. And this is kind of covered in more detail in the instruction manuals, but there's some kind of default values in there that we used for the pilot study. And then there's of course the last one there is about kind of the bank station scenario. So you really have to make a choice as to which flow scenario you're going to use as your kind of bank full scenario when you do the analysis. It's not necessarily easy to pick something that's applicable across the board, but that's obviously the ongoing debate amongst hydrologists as to which to which scenario you should use in the different situations. But the other things to note too about running the tool are you will need to have an installation of HECRAS kind of on your computer to run this. It won't kind of open up and show HECRAS when it works. It'll kind of happen in the background, but you'll need to make sure that Excel has access to that kind of the HECRAS library of objects. So there's a little bit of a step-by-step here in terms of how you go into Visual Basic and make sure that the HECRAS reference is ticked basically in that list. And as you work through and want to analyze cross sections or assets, there are a couple of tables in a couple of the sheets of the spreadsheet where you will need to enter in kind of a true in a column to make sure that that asset gets analyzed. This gives you kind of control over if you want to run one at a time, you can put a true in the column for one asset at a time or cross section, or if you want to run them all kind of as a batch sequentially and then kind of have it review all the results at the end all at once, then you can populate that column with all true values and then run everything at one time. So that kind of gives you that control to do that. Next slide, thanks. This is just a bit of I guess, a preview of the output that you'll see for cross sections. So there are kind of two different types of output. There are kind of tables where you have like one line per cross section, and that is kind of the output table. Then there's a report which has multiple lines per cross section, and each line represents one of those flow scenarios that we analyzed using HECRAS. So in the output table, we'll see the bank stations as defined in that scenario that you selected reported out next to each of those cross sections, and then in the report table we see almost all of the other results, such as the water surface elevation and velocities and things like that. So what you'll notice is that there's also a couple of spots for other things to be reported. So I will go into a little bit of detail on the overflow depths. So some of you may be familiar with the term kind of glass walling. Effectively, what that is in HECRAS, if your cross sections only extend so far in terms of the topography that you're modeling. And so when you have a water surface elevation that kind of rises above the maximum kind of value of the ground surface on either side, what ends up happening is that water kind of isn't constrained anymore by the ground surface and kind of can spread out all the way to the edge of your cross section. And then there's not really a physical reason for it to stop, but that's where the model kind of stops the volume of water being kind of conveyed. So there's kind of an imaginary glass wall at each side of your cross section as you've defined it in the HEGRAS model. So if that happens, we can detect that by comparing the water surface elevation to the topography of the cross section, and then this gets flagged here and tells you that there is some number of feet of overflow happening on either the left or the right hand side of your cross section, and it kind of pulls the predicted water surface elevation down to that kind of topographical high point, because there's no real physical constraint that you're aware of that is actually forcing the water to keep rising, right? There's potentially an infinite distance that water can spread out beyond where you've defined the cross section. So we don't want to over predict the water surface elevation here and kind of artificially inflate our results, but we are going to flag it to make sure that when you look at the results, you can see, okay, there's an overflow happening. We need to look at the GIS, and maybe we need to make that cross section a little bit bigger and find where there is some sort of geographical feature which is going to constrain the water in these kind of higher flow scenarios that we're seeing in the results of the modeling. So that's kind of an important thing to pay attention to. And then in this kind of group 5 area on the right hand side, there's also some kind of very rudimentary kind of, I guess, trend checking that we're doing. In some instances, HECRAS can have a bit of trouble just resolving some of the equations in terms of transitions between flow schemes and things like that. So every now and then, it kind of in an unavoidable kind of way, an unpredictable way, HECRAS will return kind of a bit of an outlier of a result, and you'll see a graph which is quite nice and expected, where flow and predicted water surface elevation kind of have this proportional kind of increase, 1-for-1 type of thing. And then there'll be a result that kind of does not at all fit with the trend. So what we're doing here is kind of looking at the trend and then trying to identify, is it as expected or not? And then if there's one that gets kind of detected as an outlier, so to speak, then we'll flag that, and as a first step, kind of interpolate between the two nearest flow scenarios. But those always kind of deserve a little bit of review to make sure that there isn't anything more substantial going on, and that there isn't some sort of other issue in terms of the HECRAS model itself. Next slide, thanks. So again, this is the results for an asset. When you run an asset, you get an output table and you get a report table. On the output table, there's a little bit more involved because there's some more information about the geometry of the abutments and also the vertical geometry of the obstruction that the water is passing over or through. And so we also kind of capture any errors that HECRAS or that the tool tracks. If something happens in the processing that we're doing, gets flagged, and we kind of give a bit of a description in the table here. So the main areas to look at here are going to be just making sure that, obviously, if there's any errors, we can take a look at those and diagnose them. And then if there are any kind of odd outputs from the perspective of the geometry, then you would want to look at those. But for the most part, these should be pretty straightforward and are basically informational and get passed on to the GIS. On the report table side, there are multiple sections here that are only used in the case of culverts and pipes, or bridge culverts and pipes. The idea behind that is, as Greg was referring to, we want to make sure that we're accounting for any attenuation that happens through kind of upstream storage behind these particular elements. So the way that we do that is to run a very simplified but still valid method of kind of time series analysis, where we look at how the flow would be attenuated through that storage, and we adjust the water surface elevations and the discharge basically through the culvert based on how the volume behind the asset fills up. And the kind of stepwise analysis is part of an output file that we produce too. So you can look at that output file and kind of graph it and make sure that you know, you validate that what you would expect to see there is happening. But it's not covered here, but that is part of the instruction manual as well. And obviously, again, we have the overflow situation. So left and right overflows are flagged in this table as well. And we have finally kind of an adopted water surface elevation based on the analysis. Next slide. Thanks, Chris. So after you've kind of looked at the inputs, run the HEC-RAS model, kind of generation tool, and then validated the outputs and kind of checked that they're as expected, the last thing to do is export the information so it can be used in the post-processing. So the way we do this is basically through an Excel query. And when you refresh this particular query, it kind of draws on all of those tables that are providing the output in different ways and kind of consolidates it all into one attribute table, which is then easy to join into the GIS environment and then use from that point onwards. So in this instance, we'd refresh the query table, and our recommended kind of process is to kind of copy the contents into a blank workbook and then save it as a CSV. You probably don't want to try and save this rather large workbook as a CSV because there's a lot of tabs in there, and it will have problems trying to figure out what you wanted to include in the CSV. So it's best to just copy the values out into a blank workbook and just save that as a standalone CSV file that can then be joined into the GIS environment by itself. If that's basically my slide. So if there's any questions on that, please speak now.
I think maybe in the interest of time, we'll hold questions till the very end here, and just try to get through the different sections. So we'll go back to Greg here briefly to talk through how that gets brought back into the GIS.
Yeah, so as Pete just demonstrated there, it all comes out of the hydraulic modeling tool, really neat. It's basically just one CSV file that's a table, and one row for each of the assets that you fed into the hydraulic model to begin with. And each of the columns in that table represent one of the many metrics that Pete's hydraulic tool is calculating for that asset. And it also includes columns that give you metrics for that asset's upstream and downstream cross section. For instance, what the water surface elevation is going to be at each of those cross sections, as well as the asset itself. So once you have that table, you can join it in GIS back to your your bridge points, your pipes, and your bridge culverts, and you could also join it to your to the road elevation profile points to do some further analysis. And it really gives you the flexibility to do whatever you want, really. Just for the sake of this presentation, I'm showing you just for this one particular pipe that we've been looking at, where I take Pete's output and I say, hey, let's look at the 500-year return period event for RCP 8.5 for the late century time period. And Pete's given me the water surface elevation at the asset there for that particular, for the flows for the flow associated with that scenario. And basically taken that water surface elevation, and I've calculated the delta along the roadway there to determine what the depth of flooding is going to be for that event. So those are the spectrum of colored points there indicating what the depth of flooding is going to be at this pipe for that event along the roadway there. And you can see that for this scenario, all the flooding is confined apparently to the immediate vicinity of the pipe there where the stream is conveyed. That's it.
Okay, Josh, we've been talked through phase 2 here and getting the inputs together for the risk model, specifically the asset data inputs.
Yes, thanks. Thanks for handing this over to me. So right, we're going to kind of take we're going to take a sort of a change here. All of the data that we've been collecting so far, hydraulic information, the geospatial information, we want to bring it together, and ultimately we want to feed it into our risk model where we can estimate costs related to damage from flood events. So the steps I'm about to speak with are very much kind of a research based. It's a database exercise. It's less geospatial, although we do have a few geospatial tools involved. And it really becomes the overarching message here is that we're attempting to relate the roadway characteristics, the culvert characteristics, the pipe characteristics, and bridge characteristics, and we want to assign costs to those. And so we call those replacement costs. And so I'm going to speak through some of the approach that you would go through to estimate costs for each of these asset types. So this first slide here, this talks about the roadway characteristics. So these are the approach roadways to our assets. And so this does have a geospatial component in it, in which we've acquired. We've worked with the U.S. Department of Transportation Highway Performance Management System, and so MnDOT has this information available. These are GIS files, and then they have a whole host of characteristics about the roadways. So some of the I'm going to list here on the left some of the characteristics that we're concerned with when it comes to estimating costs. So we want to have an understanding of the lane count. So how many lanes are there? We want to have an understanding of the width of those roadways. We want to have an understanding of the pavement material, the condition of that pavement. Again, because earlier in the presentation, we said part of the risk model is around estimating costs related to pavement delamination. We want to understand the shoulder type and width. Likewise for the medians. This highway performance management system also provides this information on car and truck volume, which will be important for the detour routing that we're going to talk about in subsequent steps. We also want to have an understanding of the presence of embankments. So is the road, is the approach roadway or the asset itself that we're concerned with on or near an embankment? That piece of information is not available through the Highway Performance Management System GIS data that we can acquire from MnDOT. WSP has developed a methodology to detect and extract embankments from the LiDAR digital elevation models. So if you can imagine looking at a map and you see symbolized by hillshade, you can see, you can see hills and you can see the topography. So we have a methodology to automate the extraction of those embankments and to associate those embankments with the roads and the assets of interest. That whole methodology we're not going to go into here, but it's scalable. It's something that can be applied statewide, not just for a single asset, but that's statewide. And our guidance documents talk about applying those tools to extract embankments. So this is kind of a novel technique. So with that, we want to understand the volume of the embankment and what that embankment material consists of. So and some other information that's important from the Highway Performance Management System is the federal functional classification. We may be missing data. Data's never complete. And so this helps us to sort of classify and correlate in the absence, if we're missing information, this helps us to find roads that may be similar and allows us to gap fill with some reasonable estimation of what the roadway characteristic is. This last item here that I've listed is called fixed costs. This again, we're estimating costs, right? Damage costs. This is not from the HPMS management system, but there are some assumptions that we've made around some fixed costs. So this is if you're cleaning up debris after you have a flood storm event. That debris may be construction debris. It could be trees, and so a whole host of debris cleanup. There's also costs associated with mobilizing, so to an event for the cleanup. And so those costs were agreed upon for this project, have been agreed upon, but they are dynamic and can be changed and, you know, for the particular setting that we may be working with in the future. Quickly, the graphic on the right is just an example of, okay, we're working in GIS. We want to automate procedures. We want to scale this up so it's not just the one-off. This would be an example of a series of GIS models that any GIS person could go through in sequential order and ultimately arrive with a roadway centerline file with a whole host of the characteristics that we need for estimating costs. And I won't go into the details of all of that, but it's documented in our guidance documents. Next slide, please. Okay, so we just talked about the approach roadway and the type of characteristics that we're interested in when estimating costs. Likewise, we need to go through the same exercise for culverts and bridges and pipes. So here I'm just going to talk about culverts and bridges briefly, and just I'm going to identify the characteristics that we're able to estimate costs for. We know there's a whole, you know, this is not totally complete. In fact, maybe in future versions, and as this evolves and grows, we may be able to come up with more advanced and sort of a more robust cost estimate. But currently, we're estimating costs for the presence of riprap apron, if that exists, around the culvert. We want to know the geometry of the culverts, like the presence, the count of the culverts, and the geometry of it. We also want to know something about the material and the condition. Likewise, for bridges, we want to have an understanding of the characteristics of the main span of the bridge, the structure type, and the presence of piers, and the surface pavement material and condition that's associated with that bridge. Most of this information is available from the National Bridge Inventory and also from MnDOT's asset management database. So there's some data mining as I let off. This is kind of a research exercise to collect this information, but it is very much a database driven exercise. So the message here is these are the characteristics that we're looking to calculate costs for in the presence of culverts and bridges. Next slide, please. Okay, so this is kind of a busy slide. The next few slides are going to be a bit busy, and I don't want to get into the exact details. Maybe on this slide I will, but the subsequent slides we won't look at the exact numbers. But the message here is that MnDOT has a publicly facing database that provides unit costs for awarded contracts, and it's broken down at a very granular level. And so this is an example of how you would mine that information, that data, pull out costs, and then associate that back to the characteristics that we just spoke about on the previous slides. So to lead off, given an asset's physical characteristics, the goal here is to estimate a repair and replacement cost. So let's look at an example of how you go about doing that. Okay, so we've assumed that there is an embankment present for the asset. And so now we want to have an understanding of what those costs would be. So the line items that I've highlighted in yellow, we have several to look through when we talk about embankment. And so this is sort of a cost actuating exercise. And so we've chosen 2 line items. And as you can see, the right-hand column talks about the contract occurrence, and those tend to be very high. So that's sort of an indicator of, if we needed to choose a representative example, which would we choose? And so those 2 are dominant. And so we've combined. We've basically taken a weighted average of 2 line items, and at the end of the day, we've estimated a cost of $13.19 per cubic yard of embankment. So we would go through a similar exercise for this for pavement, for shoulders, and for all the other characteristics we're interested in. And so this is not necessarily an automated approach yet at this point, because there needs to be an understanding of the proper line item that we want to be pulling when we're estimating costs. So this piece is a little bit time consuming, but it is scalable, and it's very much a database exercise and research driven. Okay, next slide, please. All right, so again, I said these few slides are a bit busy. So the message here is this would be the database that you would get for the roadway component. So on the left-hand column, we have our asset IDs. And so you'll see some of these asset IDs are repeating. And so we just kind of read across the top here and just sort of get a sense of what this database would look like. We have an understanding of roads, what type of road it is. We have some cleanup costs associated with that particular section of road. We have some characteristics of the driving surface. And so we have an understanding of whether it's a dual carriageway, the surface area of that driving surface, the number of lanes, the lane width. So likewise, we actually have multiple layers of pavement, right? So that's very common in roadways. So we have some repeating information. So for the first profile, we have some characteristics. For the driving surface pavement layer 1, we have some characteristics. These characteristics are about the asphalt and pavement, what the material, what it's made up of. We have some unit costs with that. And again, we achieve those unit costs by using the bid letting database that I just referred to in the previous on the previous slide. So just sort of scanning across the headers on the bottom section of the table, we have some understanding of the medians. And the reason why there's nothing populated for these assets is these particular assets did not have medians according to our HPMS roadway database. We have an asset that has a curb. It's a raised 6-inch curb, and that unit cost is $29. And so we can come up with the total cost based upon the geometry of the curbs. We have some understanding of the shoulders, that's left and right shoulders, and some descriptions about those. And likewise, we have an understanding of the embankment fill material. So again, we've just combined the roadway characteristics with the unit costs, and we put this into a tabular database. Next slide, please. Okay, so we've done all of this exercise to associate characteristics and properties and costs, and now we kind of want to condense this down. So this information, this table would actually be a table like this, a little more robust, but a table like this would actually be fed into the subsequent cost and risk model that we'll talk about in the next section. But if you look across the headers here, for each of the assets, again, we have an understanding of the presence of vehicular traffic, total embankment fill costs, debris cleanup costs, different costs associated with the driving surface layers. And then, let's look to the bottom row in this table. These numbers are not absolute. Remember, we're estimating costs, and there's a lot of other factors that go into building a highway system and repairing and replacing it. But these are the characteristics. When we look at kind of a relative ranking of comparing different assets and trying to make decisions in the future in terms of where we want to prioritize our time and our money, then we can look at these numbers as a way to sort of relatively get a sense of how maybe the cost and vulnerability of one asset compares to another. But again, the bottom item, has different costs ranging from, I think we have some numbers there around nearly $8 million for, and so forth. Okay, next slide, please. So that was the roadway kind of cost model and the tabulation that will be fed into the risk model. And we need to do the same thing for bridges. We need to do the same thing for culverts and for pipes. This would be a snippet of the input parameterization table that goes into those risk models. A busy table, but the goal here is to sort of look at the yellow highlighted columns and to see sort of, okay, yes, we have a good sense of, we have a cost estimate for bridges for the bridge total replacement cost for that particular asset. We have a cost for the superstructure replacement, and we have a cost for the substructure replacement. And so all of this is important when we go into the risk model. We kind of have that same, the same theme here when we go to bridges and culverts. And so I won't go through those costs. We can read these here, sort of what's important, and likewise for the pipes. So again, these are the input parameterization tables that will go into the risk model and provide all the costs that are necessary at the end of the day. Next slide, please. Actually, that was my last slide. In the interest of time, we're going to hold questions on that. And I think a lot of what I just spoke about for building those input parameterization tables will begin to unfold as Tim begins to talk about how we use that information to estimate costs and damage. Thank you.
Thanks, Josh. All right, so yeah, I'll talk about the user data inputs. So Josh was talking about these costs used to estimate damage costs paid by the agency, and I'll talk about the user cost or the detour related costs that are borne by the users of the system. So next slide. So for this, for user costs, we're using incremental detour time and distance to multiplied by essentially the ADT or volume to get a sense of, what's the dollar per day, user cost for each of these different assets. And so there are a few components of that. The key part of that is really the detour routing and estimating what that incremental detour route looks like. And so we do that in GIS using a tool that uses network analyst, the network analyst license and package, and a routable network. So for that, we used the Esri Streets, free version of the Esri Streets network. And so we get into in the documentation how you can run that tool. There's a few different scripts involved. I'm just going to try to breeze through a little bit because I know we're close to time. So each of these X's on the map, so this map is showing that routable network for the entire state of Minnesota. And each of those X's shows the location of one of the assets we're looking at. And so to run this detour routing tool, one of the first steps is just to associate each of those assets with a segment within the routable network. You can go to the next slide. And so this is just kind of a list of instructions. I'm not going to get into too much detail there, but essentially what we do is then once that is associated, an asset has been associated with a particular segment of roadway, we put a barrier across that roadway in this detour routing tool. And so the X here on the map, shown in blue, represents a culvert or a bridge that we looked at. And then when that barrier is closed, we look at where users could depart from and turn back onto the roadway that of interest. In this case, I'm not sure what the route number is. Can't see it, and I'm forgetting what it is. But where a user could turn off of and back onto that roadway if it were disrupted during a hazard event. And we run using the routable network, find the shortest path between those 2 points, which would be in green if that's the detour route. And then we look at, well, if there was no detour and that the roadway was open, what's the distance and the time associated with that route between those 2 points? And the difference between those two is our incremental detour distance and time. There's a little bit of manual review required, and the tool tries to flag segments that do require manual review based on some of those results. But really the output of that is this incremental detour length and time. You can go to the next slide. And then, another component of this is we need a monetized per minute and per mile costs for autos and trucks, and those will be aggregated with the auto and truck AEDT for each segment and the incremental detour distance and time for each segment. Okay, and so this is a spreadsheet, and this is, Philip, you had kind of asked about how you'd update the results based on if these parameters change, like the value of time or the discount rate that MnDOT uses. And so there's a spreadsheet in here that takes these inputs and calculates these per minute and per mile costs. And that's a screenshot there from that. And so that could be adjusted, and then those cells shown in orange could be adjusted, and then that would output new values in gray there, those gray shaded cells. Next slide. So then there's a different spreadsheet that takes those dollar per minute and dollar per mile costs that I just showed, combines it with the auto and truck ADTs and the detour incremental time and distance. And the output of this whole user cost exercise is $1 per day user cost for each of the assets. So it's like a unit cost. Essentially, if an asset is closed for an entire day, what's the total user cost for that 24-hour period? In this graph here just shows those assets and cost per day for each of those. 4 minutes left. We'll turn to the risk model. I just have 2 slides here, and really it's more focused on the kind of the mechanics of how to run the tool so that you're able to rerun it. The risk model essentially takes all this information, and Chris gave a good overview at the start, takes all this information on exposure that Greg and Pete talked about. It says, we have this information on exposure for a discrete number of return periods and a discrete number of years. It interpolates between those so that we have a set of probabilities of different flood events occurring for each year that we're looking at, from 2100 or 2021 to out to 2100. And then it basically uses that information on probability of events to simulate, what's our annual maximum event within each year. And it does that randomly. It picks from those distributions randomly 500 different times. And so we have like 500 different sets of what the future looks like for both of these climate scenarios. And so the output of that are these annual maximum events. Those annual maximum events, say flood depth or flood velocity, all these different exposure metrics, are then applied to estimate damage costs and disruption lengths using all the methodology documented in the risk model methodology memo. And so there's all these different mechanisms for how that we've touched on during this webinar for how that occurs, whether it's pier scour, abutment scour for bridges, or deck damage, or pavement delamination. And so those equations and formulas get applied here, and we estimate basically the percentage of an asset that is damaged, and that gets multiplied by the replacement costs that Josh talked about in his section, and by the dollar. And another output is the kind of the disruption length, and the disruption length gets multiplied by the dollar per day user cost that I just talked about. And so really what the risk model does is just aggregate all this information together. And it's based in a couple Python scripts that you can read about how to run and what variables you'd need to update in our documentation. So it uses all these, the inputs are essentially these CSV files, and it outputs a table as well of the results. And you can go to the next slide, Chris. And so these need to be run in a certain order, but and separately for each asset class, you need to run the road one first, and then you can do the bridges and culverts. The culvert risk model is the same for pipe culverts and bridge-like culverts, so that needs to be run twice. And finally, once we have these, costs for each year for the agency and to users, we tally those up. We discount them based on the year in which they occur. We use a discount rate of 0.07% because that's the MnDOT guidance, and sum those across all the years. And that gives us our final output, which is our expected life cycle costs for each asset, our do nothing costs due to flooding. And so that's generated for each asset and for each climate scenario. And that's the output that can be used in all those different ways that Chris talked about at the beginning of the presentation. And so that comes in a tabular form. It can be joined to GIS data. It can be charted like the chart shown here, where we're showing costs for different assets in for RCP 4.5 in blue and RCP 8.5 in red, and the dark shading shows the agency costs, and the light shading shows the user costs. And one of the key takeaways is including user costs is really important. It's typically the cost, depending on the asset, especially if you're in a heavily traveled road, user costs are significant. They make up a significant portion of the results. And so if you're trying to make the case for adapting something or investing in infrastructure, looking at the user costs is really key. I'll stop there and hand it back to Chris.
Okay, thanks, Tim. And obviously we're at time here, so I have just one quick slide, and then I can stay. I don't know if others until 1:15 if there are questions. Please stay if you can. If not, then we understand. Sorry that this has gone a little long. All right. So just now I wanted to mention before we cut the questions is next steps. And currently we're planning sort of a phase 2 pilot, if you will, this year. And the goal of this is to pilot test the methods that we just walked you through to develop sort of perhaps a per asset level of effort estimate for what it's going to take to do this whole process. And that was hard to get from this initial effort to set everything up, because so much effort was spent in the setup. It's not really reflective of actually what it takes to run it. So this pilot study will hopefully give us that information. And there is some opportunity as well to make some enhancements that may be needed to improve the accuracy of the results. The focus will be on District 6 in the southeast part of the state, and we intend to kind of roll this out on a county by county basis, starting with Dodge County, Steele County, and Houston County, and just see how far we get based on the budget we have. But we'll check counties off the list as we go. And then the hope is that perhaps using the cost estimate that's been developed in this pilot, that a statewide implementation could be advertised and budget determined for that and advertised or done internally in the year 2023 and or further into the future. So those are the next steps. And yeah, welcome any questions. Obviously, a lot of material here, a lot of detailed work. So we'll try our best to answer any questions you have. So
I think it might be good to point out, like one of the ways we would use this data is on that risk screening number of how much it costs for the do nothing costs. And that's a way to basically, if we have that ultimately at some point in BRIM and TAMS, that number then essentially is how you could sort and say what's likely the most highest priority in the screening level. So that's kind of one tool we can use to start actioning this data. Also, the second piece is kind of presenting the do nothing cost on a global statewide scale of we do nothing, what's going to happen. So a couple things I wanted to point out right off the bat as of how we would use this data. So.
yeah, thanks, Chris. That's a good point. I mean, you can aggregate the data to give some sense of, hey, this is the issue we're facing, and the costs are a very rough sense of what those costs might be. Dear legislature, can you provide some additional funding for adaptation or something to that effect? That's a potential use as well, is to aggregate and not just look at individual assets. So,
and also the funding already provided, like with the Protect, is finding ways, and I'd love to have that data to help kind of prioritize some of the areas we think are like our worst case right now. But until we have that, we really don't have kind of flying by real world observations as opposed to some kind of screening level that can be a bit more defined. And obviously the real world is dependent on how much precipitation hits which assets too. So this kind of helps improve that into more of a statewide analysis.
Yeah. All right, so some questions about all this material that was shared by those who are able to remain. Any questions? Well, assuming there are none, then.
Ruth, did you have a good one about? She asked me during the meeting separately about. I think it'd be good to point out her question on looking at viable detours. The fact that we're really looking at as individual assets as opposed to multiple assets being affected by an event, and that we did do a factor for kind of extreme events to try to say that it's going to take longer if there is a big event to fix something because multiple assets are likely affected. I think that would be a good one. She asked me privately. That would be good for the chat as well, or the full group.
Yeah, I'll start with that, and then maybe we can turn it over to Tim to add more detail. But yes, so obviously when you have a flood event, typically it doesn't take out just a single asset or affect a single asset. You have a whole area that's affected. In this sort of version 1.0, we have a little bit of blinders on with respect to that in terms of, we're sort of looking at it asset by asset. And as Chris said, for the detour routing, we don't consider those cumulative network effects of, if multiple assets are down, what is the detour at that point around each asset that's affected. And this is where Tim can elaborate. There is the possibility perhaps to enhance things to do that, and we are doing that with another client in Massachusetts. But it's another sort of level of effort to do that. To your point as well, Chris, you noted that there's other implications if you have several assets that are down beyond just the detours being potentially longer, and that it could take longer to repair and assets because you have that many to address, and there's only so much capacity to do that. And so there is a factor in the risk model that does account for, for at bigger events, the higher return periods, the ones that the less frequent, bigger storms, the basically, sort of as a sort of rough proxy to make some of those costs higher. In that for those storms, under the assumption that those are going to be the ones that tend to have bigger network effects if they were to happen. So let me turn it over to Tim to just, if you have any further thoughts on that sort of cascading effects of.
Yeah, nothing major, and I didn't actually hear the question, but I apologies. But yeah, if you wanted to run, I mean, if you wanted to capture basically, how detour routes would be affected by hazard that affects multiple assets, you'd need floodplains. You'd need some sort of polygon representation of the hazard that you could feed into this. You could basically use as a barrier in Network Analyst in ArcGIS, and then calculate detours around that. So that would account for not only which part of the roads of interest are flooded, but also which roadways in the surrounding network are flooded as well.
And that is the sort of the more involved effort that we're doing in Massachusetts, is to make those floodplains and get that broader sense. But as you all are familiar with, on this project, the focus is just at the crossing points of the bridge, of the stream. So the bridges, the culverts, and the bridge and the pipes. So what we're doing, perhaps there's a sort of a middle ground too. That's an option to. Ideally, you'd have the floodplains as well, and then because there could be impacts to a roadway, even if it doesn't cross the stream, it could be just parallel to it that you'd want to account for in your detour modeling. But there may be sort of a middle ground there too, with if you continue to just want to keep it where you're looking at the assets at the crossings of the streams. There could be a way to kind of string together, if let's look at the 100-year event, for all the assets and see which of those would be affected, and try to put a detour around those, considering multiple places of blockages. So I think there is sort of a middle ground approach as well, using just without going all the way to the floodplains, even though, as Tim was saying, that would be sort of the ultimate way to go. So I don't know if that answers your question, Chris, or the other person that asked it, but hopefully gives some sense of things. And again, this is version 1.0. Things can certainly be extended and refined in the future as resources allow.
This is Ruth. I was the one who asked the question of Chris. Thank you. Yeah, in 2010 we had detour on detour on detour. So that's why I asked that.
Yeah, it's definitely the real world. That's what happens, right? So I think this is still, in defense of the version 1.0 that we have here. I mean, this still gives a sense of, for any given asset, here's the redundancy of the network in the vicinity, and some sense of, based on the travel volumes, it gives a sense of this location is it's in a better location in the network.
Chris, if I may.
Yep.
I think the other thing too is that because a big part of this is a GIS application, there's always going to be the ability to map it and map the disruptions and map the outages, and allow the human user to see that image of the mapping of where there's problems, and start to realize when there's a cluster of challenges in a small geographic location, which that sort of interface is harder to program, but the human brain is good at it.
Yeah, that's a good point too. You can always take a look at it, and maybe you bump up if there's a bunch of assets that are at high risk in a clustered area. Maybe you give those a little more weight in that prioritization of where you take a closer look and try to make some adaptations. But I think the way to look at it is, you know, what we have here in version 1.0 is sort of the minimum costs, you know, without considering all those other potential chain reaction impacts. And so I think it's still a good starting point, and still gives some good sense of relative priorities, but certainly could be improved upon. Probably time for maybe one more question. Are there any more burning questions out there? Right, hearing none, maybe I'll turn it over to Siri to close us out, if you're still on, Siri.
Yeah, I'm still here, and I don't have too much to share at the end, other than thank you so much to Chris and your team for giving this presentation. It's so helpful to have an understanding of the robust methodology that was used in this first phase of the research, and thanks to everybody from MnDOT who stuck around, especially a few minutes over. We will be sharing the recording, so you can look for an email from me in the next week or so with a link to the recording. And I think with that, we can wrap things up. So thanks again, everyone.
Thanks, everyone.
Thanks all.
Thank you.
Yeah.
All right. Have a great day.